having very great academic and research record, Dr. R. Rajeshwari Madam, who is very sincere and dedicated. On behalf of all the participants, I welcome you, ma'am. I am having great honor to introduce Dr. R. Rajeshwari ma'am. She has completed her BE and ME degrees with distinction in the year 1995 and 1998, respectively, from Tyagaraja College of Engineering, Madurai. She has completed her PhD degree in the year 2009 from Anna University, Chennai. Her area of specialization, power system engineering and soft computing techniques. Currently, she is guiding 5 research scholars towards PhD. She has guided 13 candidates towards PhD. Her research publications are 60 in international journals and 3 in national journals. Her research publications include IEEE, IET, that is her research works are published in reputed IEEE and IET journals. She has delivered nearly 50 lectures in the field of her research domain. She is the active reviewer of IEEE, IET and elsewhere journals. She has successfully completed 3 research projects worth rupees 50,000, rupees 1.5 lakhs and rupees 3.5 lakhs. With these few words, I welcome you, ma'am, and I wish to hand over the session to her. Madam, please proceed.
Thank you, Nyanambal madam. Thank you. And at this juncture, I would like to thank the coordinators of this particular program, Atal sponsored faculty development program on artificial intelligence foundations for power systems. I thank Dr. K. Nyanambal and co-convener, HOD of AAA Department of KLN College of Engineering. So to deliver a lecture on the topic application of ANN to power system. So I'll be sharing the screen now without wasting time. Shall I share my screen, madam?
Yes, ma'am, please proceed.
Yeah, thank you. Hope my screen is visible to you all. Can anyone please acknowledge this? Can you see my screen, participants?
Participants, please interact. Yes, ma'am.
Okay, thank you. So only coordinator is giving a response.
Yes, few participants have typed in the chat box. Screen is
visible. Thank you. Thanks for your response. Okay. So the title allotted to me is application of artificial neural network to power systems. So as per the schedule of this program, in the morning, even in the morning session, some of speakers have talked about this ANN, that is neural network, artificial intelligence, which comes under this domain. So I think it is not necessary to start up with the definitions or the fundamentals about this artificial neural network. So I'll start with a particular network which is being applied for many of the power system problems, for solving many of power system problems. So we applied actually one of network called a feedback network, especially for many of power system problems like solving of load flow equations. Then we applied it for control application. That is, control means as far as the power system is concerned, immediately will be coming in your mind is AGC, that is automatic generation control. or simply ALFC, automatic load frequency control. So in the designing of controller for this control loop application, so we employed this neural network, feedback neural network for that purpose. And also for parameter estimation, we employed this. And one more application of this particular feedback neural network is for special protection scheme, for implementing special protection scheme for especially for identifying high impedance fault also we applied. So completely we have applied this particular neural network for many of the power system problems. So that's why I confined my topic as Hopfield neural network, where Hopfield neural network is one such feedback neural network. So we followed this Hopfield neural network for solving many of power system problems, and we got publication in reputed journals also. So through our research findings, we got published, that is we have our research work being published in many of reputed journals. So thanks for giving this platform to share the things which we have found out through this research among you. So thank you, madam, thank you. And so let us get into this topic. So the content of my presentation is about generalized Hopfield neural network. So we'll first discuss about what is what, that is the particularly about the definition and the configuration or architecture of Hopfield neural network. Then how do we apply this GHNN, this Hopfield neural network for optimization purpose, and with the help of those ideas, we'll enter into some examples. We'll work out some examples. That is very simple examples. So mathematically speaking, it would be of solving two problems. Okay, so for solving two problems, how to apply this GHNN as an optimizer. So that thing I think will be very, very helpful to you to apply this GHNN for your application. Suppose for your domain, you can even for any other domain, you can apply this thing. If suppose your domain of application is of optimization, you can directly apply this neural network for your domain. So after discussing the examples, simple examples, once you got some idea about applying this GHNN to solving simple equations, then you can get an idea how to apply for your domain now. So therefore, case studies will be apt for discussing next. Okay. So under case studies, I'll be discussing only, I'll be focusing on these two topics, that is load flow analysis, that is power flow analysis, that is how to solve the power flow equations. You know, our power flow equations are transcendental equations. So solving of power flow equations, I will be using the numerical integration approaches, right? Or numerical approaches being followed for solving power flow equations. So those equations, how to solve those equations using GHNN. So that is, I'll be elaborating that thing. And also the second case study is about ALFC, automatic load frequency control. That is the designing of controller with the help of this GHNN. That is under that particular topic, we'll be discussing about how to optimize, or optimize in the sense we are actually optimizing the value of KPKI, KD, PID controller. So at value of choosing or tuning of this controller values or variables, they are actually fixed value as far as the PID controller is concerned. But nowadays for the system to, that is we need to have adaptiveness. So to get adaptiveness in the sense for the changes in system variations. So if suppose system is subjected to some kind of variations, then there we expect the controller to respond. the controller to respond in the sense the parameter should be accordingly changed. So that we call it as adaptiveness. So for the change of a system variations, then the network here, this GHNN is giving a platform for changing or for having this self-adaptiveness. So such a self-adaptive controller has been designed with the help of this GHNN. So that thing we will discuss it. So with the results, I'll be discussing the second application. So these are my outline of my presentation. So we'll look into the network. So we know artificial neural network are being classified into two types, that is feed forward and feedback network. And feed forward means here will not be, that is the flow of data would be from one node to the final node. Where final node, I mean the output layer. So from input layer to output layer, the data flow would be unidirectional. That's it. But in case of feedback or recurrent network, there the flow would be somewhat restructured. That is restructured in the sense here during the flow of the previous data. Suppose that with the help of that thing, if any one of the node or any layer is arriving at some value, that value would be used for further processing of the next sequence of input data. So that is the main difference between this feed forward and feedback network. Okay, so recurrent means here, this is the flow. This is flow of data, X1 and X2 representing the input data. So Y is the output layer or Y is the output. And here the value, either the output or the intermediate level of data obtained through first data flow would be used for the further processing of the next flow of data. So we call it as feedback. That is nothing but we can also use the word internal memory. That is, we have to memorize that previous computation occurred at that particular node. So that has been used for the next processing. Okay, so one such recurrent network is the Hopfield neural network. And this Hopfield neural network is a recurrent network. This is actually been popularized by John Hopfield in the year 1982 itself. But by the year after 1990 only, this has been followed in our electrical domain. So this is giving a structure, the basic structure of this Hopfield neural network. And here in Hopfield neural network structure, it is a single layer recurrent network. This is a single layer. If you look into this architecture, this is single layer recurrent network. And the output of each neuron, so you can consider these circles as a neuron. So the output of each neuron is actually fed back through a unit delay element to each of other neurons. If you look at the output of each neuron, this has been given as input for other neurons. Okay, and before giving to the other neurons, it is multiplied by some weight here. Okay, so these lines are being given with some weight. Okay, that denotes the output. And so if suppose this is the jth neuron, then Wij would be the weight. Okay, weight between this thing. So here, in addition to that, each neuron actually receives an external input. Also, external input is being additional. In addition to the feedback value, it is being fed with some external input also. Okay, that is and neuron in every neuron will not have self feedback. Okay, and that would be you might be heard about the word activation function. So here also we are using activation function, and this activation function would be used at the node point or at the output point of this neuron. Okay, and this activation function, it may be hard limiting activation function, or it may be a sigmoidal activation function. Okay, suppose if you are applying this network for a continuous time operation in the sense, then sigmoidal activation function would be used. Or else, if it has been applied for a discrete time operation, then we prefer hard limiting activation function. Okay. Hopfield neural network are auto-associators. Okay, so auto-associators means here the node values are iteratively updated. Okay, this node output value are iteratively updated. That is the new state of each node. It depends only on its net weighted input. So we call it as auto-associators. Okay, so that is that node itself. Okay, it is giving the input, collectively the input to that particular node that decides what? That decides the output of that particular node. So we call it as an auto-associator. And this network is fully connected here. If you look at the architecture, this is a simple architecture. This is fully connected network. And the weight matrix here, the determination of weight matrix is one of the important tasks. Okay, so based on the application, we have to what? We have to configure this network. Okay, so the weights and the number of neurons, all such things would be decided based on the application. Okay, and each neuron is connected to other neuron. If you look at the configuration, this has been connected to other neuron by connectionist weight Wij, and there is no self connection, that is Wii. Wii is equal to 0. Okay, and one more thing to be noticed here is the weights are symmetrical. That is Wij is equal to Wji. Here I and J are representing the any ith neuron and jth neuron. Okay, so the thing is here, the main operating principle is based on the Lyapunov function, that is the stability notion. One of stability notion, you might be heard about this word, Lyapunov notion. So the operation is actually based on the monotonic decrement of energy. That is, as per this Lyapunov stability notion, it's nothing but any system possessing energy would be coming to the equilibrium point once its energy is being what? 0. Okay, so when its energy would be decayed to 0, when its energy is decaying in the negative gradient direction. Okay, that is the rate of change of energy of the system. The rate of change of energy of the system if it is decaying in the negative direction. So negative, I am specifying negative direction because negative means what? It is getting down. It is getting down. So then only the system will be what? Coming to rest. So I'm referring that rest position as the equilibrium point. So system will come to rest or equilibrium point once the energy reaches the minimum point. Okay, so that concept, based on this concept, this network is configured. This neural network, neural network is being configured. Okay, so the architecture, that is, it can also be, as per this architecture, it can also be implemented using passive and active elements such as resistor, capacitor, and operational amplifier. And by applying the nonlinear characteristic of operational amplifier in terms of sigmoidal function, the demonstrated convergence of Lyapunov function can be easily observed. Okay, and so we'll move on to this about. These are the applications of Hopfield. Various applications of Hopfield neural network can be used for job scheduling problem, matrix inversion, parametric identification, of dynamical system, then economic load dispatch, and solving a set of simultaneous linear equations. These are various applications, but I'll be focusing on certain applications and that to apply to the power system. Okay, and before that, we'll see how to use it for solving nonlinear algebraic equation. So before getting into those examples, solving of nonlinear algebraic equations, again, we'll look into the details about this Hopfield neural network. So here, to apply this GHNN, Hopfield neural network, it is necessary to formulate energy function, because its working principle, I started with energy, the system, right? The Lyapunov stability notion means we are talking about the energy possessed by the system. So if suppose if you want to solve an equation, that equation, you can consider that equation as a system, okay? So a system being described by mathematical equation. So that equation has to be formulated, has to be rearranged to get the energy function. So a new energy function needs to be formulated for the problem. First of all, this is the first point. And then weights and bias values for the network are calculated with the help of this derived energy function. So what we are actually focusing, as per this Lyapunov notion, stability notion, we are focusing our attention on the rate of change of energy. So therefore, for the formulated energy function, we need to determine rate of change of energy, whether it is falling or it should be falling. It should be falling. Accordingly, we need to configure the network. Okay, so once it is getting down and down and down to the minimum value, then at that time the value or the variables which are present, that is here the variables, I mean the unknown variables of the system to be determined. Okay, so energy function, it's a function of unknown variables here. So here energy, as it goes to minimum, it would become what? That structured, the neural network, it becomes what? Stable now. Once it reaches the very minimum energy. So at that point, the corresponding variables of the energy function are the solution. This is my concept. Can you able to follow this concept? So the network here, it results in desired solution at the minimum of network's energy. So these 3 points, if you can understand, then it is very simple to apply this particular network for any of application optimization problems. Okay, so this is the Hopfield exact architecture, neural network architecture. So here we are talking about the dynamics. So if you look at here, there's x1, x2 up to xn. Okay, so this portion we call it as a single neuron. This is known as a single neuron. So based on number of variables of the system, we have number of neurons. So n number of variables to be determined in the sense, that is x1, x2 up to xn to be determined in the sense, then n number of such circuit, or simply we call it as a neuron. So n number of neurons would be there. So if you look at each neuron, each neuron is being formulated with the help of the equation, energy equation. Okay, so from the energy equation, we are focusing our attention on the rate of change of energy. So the rate of change of energy from the energy function, that is first derivative with respect to the unknown variables. Needs to be determined. So once if you know that derivative of the energy function, so that with the help of that energy, this architecture is being formulated, is being structured. Can you able to follow this? Therefore, energy function as a function of n number of variables means with respect to n number of variables, you can do the derivative, partial derivative. Okay, so dou E by dou x1, dou E by, if suppose E is energy function, dou E by dou x1, dou E by dou x2 up to dou E by dou xn. So n number of derivative equations you will have, and for each of these nodes are nothing but they are structured with respect to those derived equations. Okay, so hope you all understand the structure now of Hopfield neural network. So it is a nonlinear interconnected system of n neurons. Okay, the nonlinear amplifier has an input-output characteristics described by activation function. Here, activation function of each neuron, we are letting this as phi of dot, where dot represents the input to that particular neuron. The most common activation function here, we are using either sigmoidal function or a linear, somewhat linear function, or hard limit function can also be used. That is purely based on your application. Okay, so this is about activation function. So as far as this network is concerned, this network is concerned, these are all the descriptions. That is, it is a network of n neuron, right? And nonlinear aggregation incorporates here both multiplication and linear summation. If you look at here, if that is for one equation, I'm constructing this network, which represent a single neuron. So if you look at this particular point, this particular thing, here, the product, see, this is product unit, it produces function Fij. It produces function Fij, okay, Fij of inputs, okay. So the function F here, it can be any combination of states. So what are the states here? X1 unknowns, that is X1 up to Xn, okay. So it can be any combination of states. So that is purely depends on the energy function formulated for the system, okay. And the output uptime from the product, if you look at here, that product, product units are linearly actually summed. Look at here, they are linearly summed here, summed at this point, okay. And this is summed through synaptic weight. Look at here, synaptic weight, Wij are there, okay. So synaptically, that is a synaptic weights W through synaptic weights Wij, it is summed, linearly summed at this summer point. And we are getting Ui. And we have this I1 also. I1 we call it as biasing value. Okay. So this component, RC, parallel component, this is to mimic the dynamics of the network. So what do you mean by dynamics here? That is, we are focusing on the rate of change of energy. That is the dynamics. That is the dynamic of this Hopfield network. So as far as this network, this neuron is concerned, this portion represents what is the dynamic of the system, of the neuron. Okay, so this energy possessed by this energy storing element, it decays, that is, it decays towards 0, and this x1 will come to a steady point or steady value once the energy comes to 0. Once the energy comes to 0. So we call it as a stable point. So at that point, the value uptime here at the output, that is output of this every neuron, they are the solution of the system. So here, if you are applying at this point, if you are applying Kirchhoff's current law at this node, so what you will get? Ci into dui by dt plus ui by ri equal to what? Equal to this one. That is sigma wij fij of x1, x2 up to xn plus ii. So that is the what? The equation describing the system. Okay, this neuron. So the output here, If you look at the output states of the network, which is nothing but x equal to phi of u. So u equal to what? Phi inverse of x. So substituting this in the previously written this equation, okay, this is the characteristic equation of each neuron. Okay, for each neuron you can write it. You can write this equation by applying Kirchhoff current law at that node, right? So if you are applying, you will get this one. So this is describing the dynamics of the system, dynamics of the neural network. Okay, so this dynamic is actually what? Deciding, that is when it is equal to 0, then you'll get the steady state response or steady state output. So the energy function for this HNN model is nothing but this one. Okay, and the derivative for the energy function is always what? Less than or equal to 0, because the system we are that is the energy function is accordingly being formulated to get what? Negative or the derivative of the function, energy function, always be less than. It is not an active source. It is not an active active source or active element. Okay, so it is not energy producing. It is actually its energy, possessed energy is being characterized by means of energy function. That's it. Therefore, its energy would become what? 0. It needs to be decreased. So this is about the structure of Hopfield neural network. So we'll discuss next how this energy function. So I'm frequently talking about energy function and the energy function and its rate of change of energy function. So how to apply it for solving a system or for solving a set of equations. So you consider a set of algebraic equation, okay, f1 of the unknown variables x1 to xn, which is equal to p1, okay, and if you have set of equations, so m number of equations, okay. So this f here represent functions, okay, they are all function of variables, unknown variables, and the objective is to find these values, these unknown values, x1, xj up to xn, okay. So to compute this using GHNN, energy function has to be formulated first. So the energy function for the proposed model is what? E equal to, I'm formulating, which is equal to Gi of dot, that is dot means here, Gi of dot is nothing but a function, it's a function of the unknown variables, okay, function of unknown variables. So Gi whole square, where I ranging from 1 to n. So what is Gi here? It's nothing but Fi minus Pi. Look at here. Fi minus Pi as per the given equation, what should be that? Fi, that is F1 minus P1, it should be equal to 0. It should be equal to 0 now, right? So we are here formulating the energy function E equal to sigma I equal to 1 to m Gi whole square. Okay, so that difference here we are considering, when you are formulating energy function, we consider square of the function. So we are introducing new function, which is nothing but what? Which should possess zero value when you are obtaining the solution, right? It should be equal to 0. But if the solution is not, that is the value obtained x1 to xn are not solution, in the sense what will happen? Maybe negative, it would be resulting some negative value. Okay, so in that aspect, we are putting this Gi as a square here. So we are very particular in formulating this energy function. Okay, so it should be of square, and for any of application, you should if you are following this hint, then will be what? Somewhat easier for solving this using GHNN. Also, we'll be introducing one more factor here, that is 1 by 2. I have been used 1 by 2 also. So this is because when I'm taking derivative, it will be resulting 2 into. So rather taking this 2 throughout my calculation, if I'm neglecting that, so for that, if I'm neglecting that, then that would be easier for me for carrying out the calculations, right? So that's the reason for putting half here. That is 1/2 of sigma I equal to 1 to n. Here, I'm sorry, I'm not given here, but for my applications, that is for solving load flow equations and for that controller design, and for other some other application like solar PV parameter estimation application, for all such things have considered 1/2 here, 1/2. So with that, I can easily come out of having this 2 in front of that those derivatives. Okay, derivative of the energy function with respect to the unknown parameters. Okay, so this is the thing. Then it is actually here, the number of neurons in the network is would be equal to what here? Number of variables. So as far as this application is concerned, the solving of the set of algebraic equation is concerned, n number of variables are there, therefore n number of neurons. Okay, so the network dynamics. So what about the network dynamics? Network dynamics is nothing but dou E by dou Xi. So Xj, here j varying from 1 to n. So Uj, so that rate of change of energy at that capacitor connected point is nothing but what? There we are getting the actual output as Uj. So duj by dt, when this rate of change of this uj is equal to minus dou E by dou Xj, then we'll get what? Minimized energy. Okay, and so the corresponding response means the output of each neuron would be the solution. See here, we are using a negative sign because when you consider positive energy function, the negative gradient decaying of energy should be represented with this negative sign. So that's why I'm following negative. So either you can follow this negative in the energy function, or else you can use it for the derivative when you are applying this network for your application. Okay, so here minus dou E by dou Xi. Okay, so this we call it as the dynamics of the network, neural network. Okay, and the transfer function, that is the function phi j, activation function is a linear input output transfer function for jth neuron, means then the partial derivative of equation with respect to the unknown, that is what we need to calculate it, dou E by dou Xi. Okay, so I ranging from 1 to n, and collecting the terms. Once if you calculated in the sense derived, once you derived the rate of change of this energy, then for the equation, the derived equation, that is the partial derivative equations, need to be what? Rearranged. That is collecting the terms of identical order. Okay, so that will result an equation, and we refer that equation as Hopfield equation. Hopfield equations. And those equations are being used for constructing the network. And that is actually just to get an idea of this Hopfield network, we are constructing that network. But once if you have got this derivative equations, then by using, that is through to simulate or to get the answer, those we are considering now those as a simple partial derivative equations. So solving partial derivative equations, it is there are a number of numerical integration approaches like Euler's method, right? Euler's trapezoidal rule, then Runge-Kutta approach. So using that can easily solve. So you have to think of one particular point here. We have started with what? Set of algebraic equations, nonlinear algebraic equations. Those nonlinear algebraic equations, now we are converting it to what? What form? Differential form. And this differential form of equations have been solved with the help of numerical integration approaches. That's it. That's it. So through solving it, you can solve for, or you can get the solution for the unknown parameter. So the thing is, the coefficients and constants from the Hopfield equations needs to be what? Determined, needs to be determined. So, and stability analysis, this is actually about a stability analysis. Yeah. So the basic notion of Lyapunov stability theory we are following for Hopfield neural network. So if suppose E of x is the energy, total energy associated with the system, which is expressed in terms of unknown parameter, that is x1 up to xn, then the derivative dE by dx, we are referring what? The rate of change of energy. Okay, so this is negative for all x value, where x is the solution vector. Where x is the solution vector. Okay, so except that equilibrium point. So what is equilibrium point? The rest point at which the energy is equal to 0. So except that equilibrium point, this will have some negative value. This rate of change of energy will have negative. Okay, so it follows that energy of the system decreases as t increases. Okay, and finally the system will reach the equilibrium point. So for the set of algebraic equation problem, what we discussed, E of x is equal to sigma I equal to 1 to m gi whole square. Okay, and gi is this one. And at any instant, the total energy in the system is positive unless the system is at rest at the equilibrium state. Okay, where here the energy would be 0 at the equilibrium state. No? So if E of x is greater than 0, that condition will exist when the solution is not arrived. When the solution is not arrived, in the sense what is not equilibrium. When the solution is not arrived means the point, the minimum point, optimized point is not equilibrium point. Okay, whereas when E of x is equal to 0, then the x value would be x, solution vector is a solution vector, is the final solution. Okay, that is the system comes to rest. Okay, so the rate of change of energy d by dt E of x is equal to, you can write it as dou E of x by dou x j dx by dt. So the dynamic of the Hopfield model, and for the as far as the input is concerned, for any other input, means for the initial value of x solution vector. So that would be uj, that would be giving uj. So duj by dt is equal to under what? It must be equal to the dynamic of the system, that is dou ex by dou xj. So this is equal to dex by dt. You can write it like this, substituting here. So you'll get dex xj by dt. This thing is equal to minus duj by dt into dxj by dt. Okay. So, and if you look at the dynamics of the system, see the dynamics is always possessing the negative sign. So that is actually giving the stability stability concept. That is that is actually fixing the stability nature of the system. Okay, that is the system, it travels towards the minimum energy point, that is equilibrium point, only when the rate of change of this energy is negative, is falling in the negative direction, negative gradient direction. So that's what here we are aiming to prove. So the dE of x by dt, if you look at here with respect to the previously derived equation, substituting here, so what you are getting is minus of this square duj by dt whole square dou phi inverse of dot dou by dou xj. So here normally this phi j, phi activation function, we are selecting this as a continuously differentiable function. Therefore
this will be resulting, this rate of change of this energy is negative at all points except the equilibrium point state. Okay, so what is the meaning? The meaning is the energy is decaying in the negative direction. Therefore, a stable system. We are having the stable system. Okay, so stability of the system is actually proved here in Lyapunov sense. Okay, so with this background, we'll start discussing about the solving of the simple nonlinear equation. So you consider this nonlinear equation ax cube plus bx square plus cx plus d equal to 0. Okay, this is a nonlinear equation. So one variable, it has one variable to be determined. X is the variable. X is the unknown variable. Okay, so how to solve this unknown variable? So here, yeah. So x is the state variable to be determined, and a, b, c, d are all coefficients. Okay. So how to solve it? First point, that is using this GHNN, we can solve it to get this x value. So first step is to formulate energy function. So I'm formulating the energy function as A equal to, so already you can take this as a function f of x. So f of x equal to these terms equal to 0. So to start with, normally when you are using this GHNN to solve any of the equation, you should try to express the equation equal to 0 form. So already the system equation is given in what? Equal to 0 form. Therefore, so that form we call it as what? We can directly take it as energy function. So E equal to, I'm taking, if suppose this is g of x, then E equal to, I'm taking minus 1 by 2, the whole square of this function, g of x whole square. So square, the reason for putting square, I already stated, because of getting the negative value. So we are putting square. So to get rid of this negative value of this resulting, when you are trying with various value of this x, so we put square here. When you are putting square, and again what? We need to put 1 by 2 here. Okay, so and I'm using negative sign for energy function. Okay, so either you can use this energy function, this negative sign here, or else for the rate of change of this energy. Okay, so what is rate of change of energy? Dou E by dou x or dE by dx. That's it. Here only one variable, therefore dE by dx. Okay, so energy function is formulated now. Next, the network dynamic equation. What is network dynamic equation? du by dt, which is nothing but dE by dx, right? As per our construction, GHNN, what is that? That du by dt, it should be equal to minus dou E by dou x, right? So this is equal to du by dt, which is nothing but dE by dx equal to minus 1 by 2. You just take a derivative with respect to x. So I'm getting this one. You just taking derivative of this energy function with respect to x. So what you are getting? This one. And rewriting this equation, that is rewriting means rearranging it with respect to the powers. So similar coefficients or similar terms are being rearranged, and we are getting coefficient for x power 5 term, we are getting the coefficient of 6a square here. X power 4, it has coefficient of 10ab, and similarly for other coefficients. And if you look at, we have a constant. What is this constant? This constant here, actually this equation is being used for constructing the neural network, right? See here, look at this. this is our equation, du by dt equal to this one. And this equation, using this equation, I'm letting the coefficients as W1, W2, W3, W4, W5, where W1, W2, W3, W4, and W5 are these things: 6a square, 10ab, and 8ac plus 4b square is W3, and this is W4, and this is W5. Okay, and this is I bias, the biasing value, the coefficient. Okay, so look at here. This equation being used for constructing the neural network. So just look at how I'm constructing the network. So W1 up to W5 have taken the weights. So this is activation function, and X is the output, and it has been given as input to the input side of the neuron, right? So look at here, W5, and then, so the first term, sorry, this term, W5 into X1, W5 into X1, this is ready now. And it needs to be added with some more terms. These are other terms. Look at here, next term is W4, okay, where it requires X square. So X square, we are constructing X square with the help of this product term, product terminal, product box, okay. So this is giving X square. Look at the input of this product block, okay. So X, and here also X. So X square, okay. So we are getting, and this has been multiplied by W4 and added. And the next term, look at the next term. For next term, for W3, we need X cube. So X cube is again obtained with the help of product block. Yeah. So getting the term added. And the next one is W2 into X power 4. Yeah. Yes. The next one is W1 into X power 5. So X power 5 obtained, and we are getting added. That's it. That's it. So the dynamics. So these are dynamics of the network is this one, energy storing element, and bias, I bias is added. So this is the network, Hopfield network corresponding to this equation. Okay. So the network would be converging to, it has self feedback. It has self feedback, and that feedback is actually given to here. And this is what? The dynamics. So once the dynamics is traveling in the negative gradient direction, would be reaching after some time, it would be reaching towards the equilibrium point. So at that point, the output would be what? The solution. The output would be the solution. So this is the architecture for this particular application, that is for solving this. So how to simulate? So this is the network. I'm just I've given it again. And to simplify the expression, we neglected leakage term after the aggregation and consider only the dynamics. So this is the dynamic equation which we considered for constructing the Hopfield network. Okay, so I should have shown this one before seeing that architecture construction. So with the help of these conventions, have formulated the network. Okay. So with the proper activation function, that is the input-output relation for the pth neuron, for any one of the neuron, that is pth neuron means here only one neuron now for this problem. That neuron of model is given by xp, that is the output, is equal to phi of up. So phi p is a function, okay, is here considered as a linear input-output transfer function. It's not a sigmoidal function because this is a matter of what? Simply solving an equation, nonlinear equation described by a single unknown variable. So we have considered the single linear input-output transfer function is enough for solving this equation. So that's why we have selected the linear input-output transfer function. And the network is actually simulated numerically using Euler method. So what is Euler method? The dynamic du by dt, you can write it as what? U of t plus, that is du by dt is a differential term. So that differential term can be given, written as per Euler's rule, u of t plus 1 minus u of t divided by del t. And this del t represent the step time, right? So with the help of this equation, that is, it has been used for this equation, okay, applying Euler's rule, and you can find this u of t plus 1, okay, and that u of t plus 1, which is what will be giving some output, and that output again given to the input, okay. So this is what actually happening. This is what actually happening to the network. Would you be able to follow this? So as far as the simulation part is concerned, we are actually we are converting the equation. We are converting the equation to simple differential equation. That's it. And the differential equation is being integrated numerically to obtain the solution. That's it. Okay, so this is the procedure of solving this simple equation. So results with the parameter, that is A, B, C, D parameter, coefficients of that nonlinear equations have been considered this one. And with this approach, that is a GHNN approach, with the initial value of this thing and U0, so X final value. If you look at this, this is the solution. This is the solution, and the solution for comparison purpose, Newton's method, its output is also being displayed here. If you look at the solution, both are same. You're getting the same solution as that of the Newton's method. Okay, so when you are solving this equation, nonlinear equation using Newton's approach, you know, Newton's approach means it involves calculation of Jacobian matrix. And also we need to take inverse of the Jacobian matrix, okay, in finding the solution. So we have a big headache of finding the Jacobian matrix and also finding the inverse of that matrix in obtaining the solution. So we are actually getting out of those steps when you apply GHNN for solving this equation, okay. So this is, if you look at the energy function, we were talked about the energy function for solving the equation. So the energy as time progress, we plotted the energy function. So the energy as time progress, it comes to zero. It comes to zero. Okay, so monotonically decreases to zero, and once this model possessing the stable dynamics, we should not use the word dynamics. Stable point means the equilibrium point, the corresponding state, the solution or the solution vector corresponding to that particular state is the solution vector. Okay, so this is showing the energy function profile for the model. And this is about the example 2. Here, two variables, that is two set of equations. Okay, so x1 and x2 are unknown. Okay, and pair of nonlinear equations. Let us see the procedure. The same procedure, but here we have two equations. So how to solve for x1 and x2? So these constants, coefficients will be given for the problem now. So how to, first step is to formulate the energy function. So I'm taking the first equation. What is the first equation? Already the two equations are given in equal to 0 form. So the first equal to 0 form, let it be G1, and the second one as G2. So G1 square plus G2 square. I'm giving minus 1 by 2 in front of those summation. Okay, so minus 1 by 2 of G1 square plus G2 square. That's it. That is my energy function formulated for the system. Okay. What is our next step? We need to take time derivative. So time derivative is nothing but du1 by dt, which is nothing but dE by dx1. That is dou E. Here, I'm sorry, here partial derivative. So dou E by dou X1. Okay, so minus dou E by dou X1, and dou E by dou X2 is what? Energy for that second neuron, because this is two neuron network, because two variables are there, two variables to be determined. So system is being described by two variables, therefore two neurons. So there are two derivative functions. So with the help of derivative functions, the corresponding diagram, that is architecture, can be structured. Okay, so du1 by dt, du2 by dt, which is equal to what? These things. So the corresponding coefficients, you can work it out. Say, look at here. So rearranging the, once taking the derivative, you rearrange the equation for getting the common terms, common ordered terms, okay, and then extracting the coefficients. And those coefficients, I'm letting this as similar to the previous problem, W1, W2, W3, up to what? These things. And the biasing will also have the bias value for both of the equations. Okay, so using these two equations, so you should know these things, these conventions also. Then only you can what? Easily write down the program for solving these two equations. Okay, so aim is to construct two neurons, right? Feedback neuron, that is Hopfield neural network, to be constructed with the help of these two equations. So look at here. So X1 is the output from the first neuron, okay, and W1, okay. Then X2 also it is needed, okay. Look at here. The next term and the next term, okay, to obtain X2 square. Then next term we require X1 into X2 square term, and it is multiplied with a W5, and these terms are all added, and this has been added with I bias, okay, to get X1. Okay, first equation is over. Second equation, proceeding with second equation. So look at here, X1, X2 are all taken out, and X1, X2, then X1 square, then X1 square into X2, then further. So we are getting this one. So network is being constructed. Okay. So the next step is the dynamics. So this is U1 and this is U2. This is the complete network, complete architecture of HNN for this particular optimization problem. So the solution of these nonlinear equations have been obtained after that numerical simulation. So for numerical simulation, that is solving of those differential equations, either by Euler's method or any other numerical integration approaches, you can solve it. Okay, and here also it is the results are being given. If you look at the X1 and X2 final value, both are very similar to the results obtained through Newton's method. But the thing is what? The main thing is we are coming out of the big headache of what? Inversion of Jacobian, formulation of Jacobian and inversion of Jacobian. Okay, so that is one of the main advantage of using this GHNN in solving this. And energy profile for this problem has been observed. So we solved these two simple problems with the help of this GHNN. We had written down the coding and we solved it, and we compared this with Newton's method. Okay, then this is actually compared. It is a calculation. It avoids this HNN. Hopfield neural network avoids the inherent limitations of Newton's method. So what are the inherent limitation is the calculation of this Jacobian matrix and its inversion. Okay, so we are coming out of this part when you apply HNN. Okay, so with this understanding, we applied this HNN to our power system problems. So what are the problems we actually applied for many of the problems, like power flow, that is load flow problem, and not only applied this power flow problem, and once we established the coding for solving power flow equations, we followed that power flow analysis for voltage stability analysis. To evaluate voltage stability, we applied it. And also we applied it for contingency ranking. For contingency analysis, we followed this power flow analysis. And so we published many papers for under this particular application. In here about 4 publications we made it for this particular approach, that is with power flow analysis using GHNN. Okay, and we applied this GHNN for the design of controller, PID controller. Okay, and PID controller for maintaining the frequency stability. So look at we are using 2 important terms, voltage stability and frequency stability. So for a system, stability is a big headache, no? That is, we have so many obstacles or so many factors which are deciding the stability of our network, right? Because, for example, nowadays we have renewable energy sources penetration. So in presence of renewable energy sources, the stability. So what about the stability of the system? Because renewable, as far as the renewable sources are concerned, there we have to sustain with such sources with the energy storage. So storing of energy, but we are lack of storage system. Okay, so in our as far as our Indian grid is concerned, there is no such facility for storing the energy. Okay, because of a highly intermittency nature of these sources, we need to have such environment, energy storing environment, but we don't have. But they are present in our network. So they are playing a vital role in deciding the stability. Okay, so stability is very, very important. Okay, as far as the quality of supply is concerned, we will be very particular about voltage and frequency. Okay, so the voltage at every point of our network should be maintained at the nominal value. Okay, and then frequency also should be maintained. So with respect to those those points, we were focused our attention on these 2 particular applications, and also we developed a special protection scheme to identify high impedance fault with the help of a classifier, that is using this GHNN being used as a classifier. But for presentation purpose, I'll be focusing on first 2 applications. So the conventional, I'll be that is the conventional mathematical approaches for power flow technique of solving power flow equations. It requires inverse. So immediately when we talk about the power flow analysis, we'll be preferring normally power system operators will be preferring what? Which method? This Neuron raption technique, because it end up with lesser number of iterations. But the computational burden, as far as the computational burden is concerned, it is heavy per iteration, as far as this NR method is concerned. So it requires, as we discussed earlier, Newton raption means we need to formulate Jacobian matrix, and then we need to take inverse to obtain the solution vector. Okay, so and numerical power flow technique, it fails to. There are some other numerical power flow approaches like Iomoto and other Euler's technique. There are, if you refer research papers, so we have many of approaches, numerical approaches for solving power flow equations. So they actually failed to perform online voltage stability analysis, but that is because of what? Some time delay in computing in arriving the solution. But if you follow this GHNN, even it can be used for online voltage stability analysis. So online means the real-time compatibility. We should have a real-time compatibility. So it is giving a quick response. This GHNN is giving a quick response, means a quick solution, power flow solution. Okay, so it can be used for online voltage stability analysis purpose. And the conventional, as far as this control application is concerned, the conventional tuning of proportional integral derivative controller, it cannot operate for wider operating region to maintain the frequency stability of the system. So as I said earlier, the system may be subjected to some kind of changes. So for system uncertainties, we need to, that is, generating station normally provided with, or conventional generating stations are being provided with the ALFC, automatic load frequency control. This closed loop control is being provided, but I suppose if there is any changes happening onto the main plant. So main plant in the sense, if suppose a plant is having 5 number of generating units, one of the unit is getting shutting down. So therefore the system inertia constant, right? The inertia constant and other time constants are getting deferred. Okay, so accounting these things, we call it as system uncertainties. Okay, we are bringing this changes under system uncertainties. Under system uncertainties, suppose the ALFC is being designed with certain value of KP, KI, KD, that is PID controller. So that would be working for what? With all such plants, all such generating units. If one of the system is, one of the generating unit is shutting down, then we need to account those cases also. So adaptiveness, we require adaptiveness. Okay, so that such kind of adaptiveness is possible with this GHNN based PID controller. That is, we brought this feature with the help of this Hopfield neural network. We designed the PID controller, self-adaptive PID controller with the help of GHNN. Okay, so we'll look into the recurrent HNN, that is Hopfield neural network based power flow analysis. So for power flow analysis, how to apply that? So far we discussed the application of this GHNN, that is HNN, for solving equations, simple mathematical equations. So let us now move on to how to solve the power flow equations. So for power flow problem, to start with the power flow analysis, so what we'll do, we have to first of all formulate the energy function. So the energy function for this HNN, I formulated, that is we, myself and my scholar have formulated the energy function as -1/2 into sigma. We have considered the power mismatches, real and reactive power mismatches, del Pi and del Qi. What is del Pi? Real power mismatch, which is nothing but Pi specified minus Pi calculated. So Pi specified means for the ith bus, the P value may be given, would be given in the under bus data. And this Pi calculated is nothing but the value which is being calculated for the initial solution vector. So if this difference, there would be some difference with the initial value. Okay, there must be some difference, and we call that as a mismatch. So that mismatch, when we arrive at the solution, for this Pi, what is Pi? Pi is nothing but this equation, power flow equation, real power flow equation, which has the passive element values Yij, Vi, Vj, and theta j and theta I. So here, this Vi, Vj, theta I, theta j, based on the type of bus, there will be known and unknown values. So the unknown value, this is a function of unknown values. So for the initial value, you can compute this pi calculated, okay? And if you are substituting that, and there would be some mismatch, and that mismatch we call it as del pi. But when the correct value of Vi, Vj, theta I, theta j, unknown values are being arrived, then pi calculated would be equal to this pi specified value. So that would be at that time that this mismatch would be equal to 0. So we are seeking for that condition. We are seeking for that condition. So that's why the energy function is being formulated with this mismatch. So, you know, power flow equation means not only with real power and reactive power. In a similar way, we have as a reactive power injection for bus. So Pi and Qi, they are representing real and reactive power injected, net injected power at the ith bus. So in the same way, you can also write this del Qi. So now we have del Pi and del Qi, which is expressed in terms of what? Unknowns. So these are equal to what? This thing, del Pi square plus del Qi square, where I ranging from 2 to n. N is number of buses. First bus would be the slack bus, okay, and to meet out losses. So here, del Pi and del Qi are the real and reactive power residuals of the system. So energy function is formulated. And what would be the next step? We need to take the derivative. So without formulating any other Jacobian matrix and any other thing, I'll be just what? Taking derivative with respect to unknown variables. So unknown variables, what are unknown variables? It may be voltage magnitude and its angle, maybe its angle. Okay, so if it is PQ bus, then Vi and theta I. If it is PV bus, then theta I alone, But the thing is, Q needs to be determined to check for Q violation. That is reactive power violation. So the dynamics of neural network, they are represent these two equations, they are representing the dynamics of HNN. So which are needed to be solved here, and we solved it with the help of Runge-Kutta approach, fourth order approach. So if you look into this, we actually derived this equation for 3-bus system. First of all, we started with the 3-bus system. We derived this dou E by dou Vi and dou E by dou theta I. And then we started with IEEE 14-bus system. Actually, we got a very lengthy derivation part, and we aimed to generalize these two equations, dou E by dou Vi, because we actually submitted the content to IET GTD, but they were asked for, that is, the reviewer have asked for generalizing the equations, so that we can able to applying, that is, generalizing the derivation part. So that's the question raised by one of the reviewer for during the very first review process, and we derived it and we solved it. We actually solved it. So this is the complete. This is showing the complete flow diagram for solving the power flow equations using this thing, that is this neural network approach. Okay. So the flow would be very, very similar. The thing is, with the initial case, that is del Pi and del Qi need to be calculated, and then energy is being calculated, okay, for all the buses. Okay, then check for PV bus. So if suppose PV bus, then check for Q limit. Okay, Q limit. If it is within limit, then calculate dou E by dou theta I. If no, then you calculate it for what? The PQ. That is not the limits are violated in the sense, then we have to set it as PQ bus now. So for PQ, and for this case, we have to calculate dou E by dou Vi and dou E by dou theta I. That's it. So calculating, computing this, and those derivative, that is differential equations, are being solved with the help of RK4, that is Runge-Kutta, fourth order. Then we were checked for what? the energy, that is dE by dt, which is less than or equal to 0 for tolerance, for checking for the convergence. And if it is lying, then we stop the process and obtaining the solution. So this is what we did for power flow analysis, and we applied it for contingency ranking and voltage stability analysis. Okay, and moving on to the second application, that is recurrent Hopfield neural network based controller for frequency stability, that is ALFC. So as I said earlier, our modern power system, it is now penetrated with renewable energy sources. Okay, so in presence of this, we have to what? Maintain for our conventional. We also use conventional power plants even now. That is, majority of our power plants are of what? Conventional, very conventional power plants. So to maintain the frequency in presence of the renewable, so has been discussed in the next section. So how to apply this HNN for the design of PID controller. So when you are designing PID controller for closed loop operation of any system, you know, tuning of this Kp, Ki, Kd value, those constants is the big headache, right? So appropriately we need to select it. So if suppose a plant is not, parameters are not changing with respect to time in the sense, then it would be okay. But if it is changing, then we need to incorporate what are the self-adaptiveness feature into this in a controller. So here, this error. So let us look into the procedure, how we uptime, that is how did we apply this HNN for designing this controller, PID controller. So look at here, this is a PID controller. So E of Kp, Ki, Kd. So these are the unknown parameters. Therefore, 3 neurons. It's a 3 neuron structure. Okay, HNN would be 3 neuron structure, which is equal to 1/2 E of t square. Look at here, E of t is nothing but error. This is reference value and this is Y plant. So E of t square. So 1/2 E of t square, and E of t is nothing but Y reference minus Y plant. So this energy function can be rewritten as 1/2 into Y reference minus Y plant whole square. Y plant, it's nothing but, if suppose system operator is T, this plant operator is T, means what is input to this plant? Input to this plant is nothing but U of t, output of the controller. What is output of the controller? U of t, which is nothing but Kp into E of t plus Ki integral E of t dt plus Kd into dE of t by dt. Right? So this U of t is being operated through this T, plant operator T. Okay, so T of this thing, U of t, is the output of the plant, Y plant. So substituting here and taking the dynamics. What are the dynamics here? Dou E by dou Kp, dou E by dou Ki, dou E by dou Kd. So they are nothing but dKp by dt, dKi by dt, and dKd by dt. So this has been obtained through this equation. So these are the equations. Look at here. So we need to find the solution of this dynamic equation, and the solution being obtained through Runge-Kutta method. Either you can start with a very basic method, Euler's approach, forward or backward, or else trapezoidal rule you can apply. Okay. So these 3 equations, dynamic equations, you can see this is the corresponding structure, GHNL. This is GHNL architecture. So look at here, 3 neurons, Kp, Ki, Kd are the input, output, and these outputs are fed back to at the input side. And if you track the path, for Kp, that would be equal to this one. So using this dKp by dt, this equation, it has been drawn here. And similarly, dKi by dt, you can track it, you can verify. Okay. And this is the model, hybrid model, power system model, which we considered for this ALFC application with GHNN based controller. And we considered like hybrid power system, that is renewable environment. Normal conventional power system with renewable environment. So renewable environment, it's nothing but it is basically injecting some power onto the system with the conventional area. Area means, I mean the power system. Okay. So the thing is here, the power, which is nothing but, this is the point at which the change in demand, the change in demand is being applied. Okay. So this is our power system, and for a conventional power plant, normally the frequency of that power plant being maintained by observing the change in frequency, and accordingly, whenever the system is observing some change in frequency, accordingly the turbine power output, that is turbine power output in the sense the control valve position of the mechanical device of a power plant would be adjusted. So if it is a steam power plant, then steam input would be adjusted by changing the control valve. Okay, so the control valve of the turbine would be adjusted. Okay, so this is actually this flow showing the modeling, simple modeling, that is the transfer function modeling of all the mechanical devices and electrical device employed for our conventional power generating unit. So in presence of this conventional power generating unit, we have considered what? This plug-in electric vehicle, and also this thing, that is the renewable energy source also. Okay. So and also we have considered the tie line power also. That is, the tie line power means the system would be in a position to meet the power exchange between two areas. So the area to which this power plant is connected may be in a position to exchange some power based on the requirement of the adjacent area, which is in interconnection with this. Okay, so those power exchange are the power demand and the power demand of this system. So they are actually imposing some frequency changes. So those frequency changes, objective of this ALFC is to what? For this change in frequency, accordingly we need to adjust the mechanical power input to the generator. That's it. By changing that, you can adjust the frequency, or that is, you can adjust means you can make this del F equal to 0, change in frequency equal to 0, and so you can maintain the nominal frequency. So that's the objective of operation of this particular loop, ALFC loop. So in this ALFC loop, we are employing some controller here. If you look at this input side, so this is the controller. So the controller, it is giving what? The change in frequency. It is actually having some transients, and to improve the transient performance, we are putting some controller. Okay, so the controller we employed, that is usual your textbook. If you look into the textbook or any other earlier publication of related to this ALFC, you may be seeing what? The very basic controller like a PI controller, or it is actually started with the integral controller, then PI controller. Okay, so there are very basic controllers being employed, but nowadays, if you look into the research papers, even control engineers, they are taking this ALFC as a benchmark problem for validating their controllers, newly invented controllers. Okay, so we have considered various cases for this LFC study, that is the changes in various area, that is two areas which are being interconnected, are imposed onto, that is onto the system, and we measured the output. Okay, these are the output with the GHNN based PID controller. We recorded the output through MATLAB simulation. So the simulation is the simulated outputs are shown here. So the outputs are shown. So you can look into this. We actually did this for with 4 different controllers like integral, PID, fuzzy-based PI, and GHNN-based PID controllers. With all this, we derived the output of the hybrid power system. So if you look at the transients, so the transients for other controllers, if you look at the other controllers, we have some oscillations. Okay, so those oscillations are actually under damping, but it is damped out once, that is after a very long time. That is reaching the steady state value is the time taken to reach the steady state value is very, very large here as far as the other controllers are concerned, that is integral, PID, and fuzzy-based PI controller. Whereas if you look at this GHNN PID controller, it comes to the steady state as quick as possible, right? So for all the cases, for all different cases, if you look at the response, the red color plot, so it is giving a better performance than the other controllers. Okay, so, and we also checked it for the self-adaptiveness. That is, self-adaptiveness means here between 2 consecutive disturbances, how fast it is accommodating. This controller is accommodating the new change. So that thing is also being checked out here. Okay, so we purposefully changed the input, that is del PD input to the system being applied at a time t equal to 25 seconds, and we observed the response. So it is quickly adapting to the next changes caused in the system, and we observed the corresponding KPKI KD value. So for a change in system parameters, means here the transfer function model of the power system. We have considered Elgert book problem, that is a 2 gigawatt problem, one of a benchmark ALFC problem, 2 area system. So there the transfer function model, that is KP, gain value is 120 and the time constant is 20 seconds. So KP by 1 plus S KP. So for that, the KP, that KP value have been decreased to half, that is 60. For that value, we looked for KPKI KD value for PID controller. See, if you look at here, at time t equal to, that is the change we caused, we have done it for the system. So under such condition, if you look at the value of KPKI KD, so you can observe the change in KPKI KD. Okay, so that is possible with the help of this GHNN based PID controller. So that is one of the main benefit. Okay. And these are all showing the transient performance of this with respect to different parameters like del F1, where del F1 is the frequency deviation in the first area, okay, and for del F2 for the second area. So transient performance means we will be considering the settling time, steady state error, and peak overshoot. So all these been observed for different controllers, okay, for different cases, okay. So these are all the output, and we also did this not only through MATLAB, we did it with the help of real-time digital simulator also. That is, we have in our lab Opal RT kit simulator. So with the help of that, we did this hardware in simulation, this hardware in loop simulation to validate our model for real-time environment. So these are the corresponding outputs. And these are the list of publications as far as the power flow analysis is concerned. These are the papers published, and for ALFC, these are the papers published in IEEE and IET papers, and these are for special protection scheme published all this. Yeah. Has any doubts, students? Oh, sorry, participants. If you have any doubt, you can ask it down. You need any clarifications? Hello.
Participant, you can ask your doubt.
You have any doubts, student, participants?
Okay.
Okay,
Ma'am,
sir.
Thank you, ma'am, for your detailed lecture on the
Thank
topic
you,
of.
sir.
Thank you, madam. For your detailed lecture on the topic of application on ANN to the power system. You have given a lot of information, ma'am, in the neural network application in the power system. Once again, thank on behalf of all participants, Atal and KLNC, ma'am. Thank you, ma'am.
Thank you, sir. Thank you so much. Thanks for the opportunity, sir.
Okay. Welcome, ma'am. Thank you, madam. Close பண்ணிக்கலாம், madam. Thank you, madam.
Yes, sir. Thank you, sir. I leave the meeting, sir. Thank you.
Okay, madam. Thank you.
Participants, if you don't have any queries, I'll leave the meeting now.